Well, as Cheryl said in the email that sent out to all of you describing the program, she wanted academics from Hopkins who work in very different disciplines to come in and talk about how the work that they're doing, how their field, how their labs work within the field can feed into issues of policy regarding climate change. And you might think I'm kind of a stretch because I'm one of these people that bust organisms up into individual proteins. And it's kind of hard to think how that information could feed back into any sort of advice that we might give to policy people. In other words, we're reductionists. We work in a field that's called Ecological and Evolutionary Physiology, and I'll explain what that is and try to give you a sense of how we can work from kind of reductionist physiological, biochemical, and molecular data out to these broader issues that deal with climate change. So the field, as we employ it, really looks at two different questions. It may give a very beautiful précis of my talk. So as far as I'm concerned, you can just put it here right now. Do that as a day. There are two more speakers. We have focused in our lab largely on temperature effects over the years. And I'll go back to my graduate student days and develop a trend that's gone on for a long, long time. The things that we look at are, as Meg said, adaptation, how the physiological systems of organisms fine-tune with particular environmental factors like temperature that they face in their habitats. And we typically work with what are called ectothermic organisms, cold-blooded organisms, whose body temperatures are often very similar, identical to the water in which they live. We're also interested in how stress, things like sharp changes in temperature, impact physiological systems. And among the questions that we address under that heading, are there weak links in the physiological chain? For example, is the cardiovascular system or the nervous system particularly prone to be whacked hard by changes in temperature? And on a broader scale, when we compare different species, we try to identify which species seem to be most endangered from the effects of climate change. So I'll talk about that in a more specialized part of my talk on the Antarctic fish. Now, one important element in any work of this sort is the time course over which the effects are occurring. And as I'll mention in my talk, we have two really different foci. One is on evolution, where things like protein stability, protein function, protein expression, and the very contents of genomes change over time. And that's been a major focus of our work. But we also are very interested in the process of acclimation, often discussed in the context of phenotypic plasticity, where the organism selectively uses the tools in its genetic toolkit to modify its body, modify its phenotype during its lifetime. So both of these time elements are very important. Now, how do we get from that sort of low-level reductionist work back up in a more integrated way to talk about global change and policy? And I think the simplest, yet I think an accurate way of looking at it is what sorts of policy-relevant predictions can we base on physiological data. And I think there are at least 4 different types of predictions. Most dramatic may be extinctions, and that will be the primary focus of my talk on Antarctic fish. Using physiological data, we can say this species is going to be a big loser with climate change. We can talk about biogeographic shifts, where do organisms occur. Meg used that term. It's a good one, because it talks about where on the globe, with latitude and longitude, there are species going to have to be, and also there's a vertical dimension out here in the intertidal zone, Rock Mountain size. Another issue with stress is things like productivity. If the organism is having to expend a lot of its energy coping with stress, it may have lower reproduction, lower growth rates. And then finally, a very interesting issue that I wanted time to talk about are invasives, because there's some very interesting stories that show that as the oceans are warming, invasive species that are themselves warm adapted are doing very well. So that's kind of the skeleton of what our field is about, and very briefly what our lab does. And I want to get now down to a more specific story, making my title Antarctic Fish in Hot Water, Their Fate Lies in Their Genes or Lack Thereof. I love this picture from Norbert Wu's work. This looks like a fish in a blended margarita. It's actually a fish called Pegophilia borquerminki living under the ice in McMurdo Sound. And this fish has a body temperature of minus 1.86 degrees all year long and for many millions of years. Well, why do we study these things? Well, partly it's what's in my genes. I'm half Finnish DNA, and when I left Minnesota to come to graduate school at Stanford, I didn't have the good sense to remain in comfortable Palo Alto. I went to Antarctica in 1963 with different colored hair and beard, lots more of that, as a matter of fact. We still go back today. In fact, Mark and Denny are going down in January with Judith Connor and Bari to do more work. At the McMurdo Station here at 78 degrees south, it's the southernmost extent of the world ocean. This shows a couple of us hard at work. Stanford, they've been paying me doing this for a long time, so keep your own life on Stanford. Anyway, the reason we go down there is to catch some of these critters. I put this slide in to show you the fish we work on. We're also expanding out to work on picnicodes and sea stars, cold herrings, and stuff like that. A lot of interesting fauna lives beneath this ice. And the fish I began my thesis work on belongs to a suborder called Nototheniidae. It's a group that represents most of the fish in Antarctica, something like 9% of the fish biomass. And what's interesting about them, they've been evolving for 14 million years in what's really a very stable ice bath, very narrow temperature range. So they've had a long evolutionary history of cold and very stable temperatures. And in my very first paper, done with Arthur Green's, a Stanford classmate, you show these fish are dying of heat death at 4 degrees Celsius, or 39 degrees Fahrenheit. It's good to have that sort of conversion for the audience. That's an awfully low hot temperature to kill things, and we're still wondering why that's the case. And going back in January, we'll pick away at that problem some more. The hypothesis that we're working on, and I'll drop it on the bottom of the slide, is kind of like the blind cavefish hypothesis, the blind cavefish model. If you're not using genetic information, they can deteriorate and be lost. So the hypothesis is that over this long evolutionary period, 14 million years, at these very low, very stable temperatures, genes that an organism needs to deal with rising temperatures can go bad with no penalty. Just like fish in a cave can lose their eyesight, no penalty. It's always going to be dark. Here, it's always going to be cold. At least that used to be what was the case. So what kind of genes do we worry about? Well, it turns out, I don't have time to go into a broad story. We're using DNA microarray gene shift technology to survey hundreds of different genes. But a very important system that's essential for coping with heat stress is a genetic system called the heat shock response. And what that comprises is a set of genes that are switched on that encode proteins that repair thermal damage. It's a repair system. And it's a very important repair system. Now what happens is that when you heat an organism, and this can be any type of organism, body temperature goes up, proteins become damaged, slight denaturation. In other words, they're just slightly cooked. Rare, but they're still cooked a little bit. At the same time, signaling systems turn on the heat shock genes. In other words, at the DNA level, a set of genes are transcribed, and they lead to the production of a large variety of proteins called heat shock proteins. These heat shock proteins repair the damaged proteins, and the organism can be back in very good shape within a few hours, perhaps, thanks to this repair system. Now, the heat shock protein system is something that used to be thought of as a ubiquitous genetic capacity. It's important in human beings. In flu season, if you start spiking the temperature up around 101, 102 degrees, you're cooking your proteins to a certain extent, and you're going to be turning on the heat shock genes big time when you get, if you get the flu. I hope you don't. I hope all these bozos on Fox News that think the vaccine is a government plot end up interested, but that's another. Well, it turns out that these genes have been lost in the Antarctic fish. So a system that was thought to be universal among organisms is absent in these fishes. They can't show the heat shock response. Just to show you one data slide, if you spike an organism, inject it with a lot of sulfur-35 labeled amino acids to get a radioactive signal, watch it make proteins. This is a little mudsucker that lives over in Elkhorn Slough. 16 degrees, they make proteins with this particular pattern. These are separated by molecular weight. Give them a 37-degree heat shock, the fish can take it just fine for a long time. And that's partly because it cranks up the production of a whole variety of heat shock proteins. Take the Antarctic fish, they can't do anything. They won't show any sign of heat shock protein synthesis. So basically what we're looking at is a situation where global warming may be a lethal fever for these fish. In other words, it's a fever that you can't get over because you don't have the tools. We're evolving in the dead end. And this is the state of Oregon's highway system. That's why we move back to progressive, intelligent Central California. So that's almost the end of the story. One more slide. How do we now go from physiology to policy? Well, I was involved on 2 National Research Council committees that put out 2 reports. And the first of these came out about 5 years ago now. And it was how can we take information from genomic type science and apply it to polar science? Not only in the case of policy, but just in helping to understand the polar ecosystem. And then subsequently, there was another NRC committee I was on that was there to design the programs for international polar year. And again, this kind of physiological, biochemical information fed into a certain number of the analyses that were projected during the international polar year to use, in a sense, physiological indicators of what lies ahead in terms of climate change. So I'll leave it there. But one more slide. I brought a handout in from a recent Pew report, which gives some kind of chilling numbers about, despite all the things that we study as science and talk about, the public's acceptance of climate change seems to be going down. That might be a good thing to discuss. I'll be impressive to discuss later on. So how do I do the time?
Good.
Good. I can't do any more slides.
No.
It's always an interesting thing to follow George, especially when you're talking about catastrophes. That's something you're going to try. I'm also the farthest of any of the people you're going to hear from tonight about connections to policy. What I do is science. I think it can be related to policy, but the connections are a little bit less clear-cut. So what I'm going to do is just talk about the kind of science that we do. I grew up as a biomechanic, and lately, actually for about the last 20 years or so, we've been applying biomechanics to ecology and what we now are trying to call ecomechanics. Basically what we're doing is using physics and engineering to explain the interaction between organisms and the environment. So we're looking at the mechanical side of things. And to give you an example, one of the things that the ecologists often think about are the effects of extreme events. Extreme events can have long-lasting effects on ecosystems. So for instance, if in your backyard a volcano suddenly appears, it's basically going to push the reset button on the environment, the ecosystem for tens of miles around that, and that can have effects that are lasting for decades, even centuries. Other things like hurricanes. One day of a hurricane can flatten a forest well inland, and the effects of that event can last for decades. I grew up in North Carolina where Hurricane Hazel came through in 1957, and you can still see the effects of Hurricane Hazel 52 years later on. Now, those are the kind of extreme events a lot of people think about when they think of ecological extremes. But those are just the sort of poster children for these. These are simple events. They either happen or they don't. But I'd be willing to wager you that most extreme ecological events don't happen from one thing in the environment going really, really bad. They happen when a number of normal things in the environment come into coincidence. So if you start thinking about these sort of compound events, you can come up with a long list of compound sorts of things. I don't have time to go into that list, though I'd be glad to discuss it with people later on. I'll just start off with one example of this, which got us interested in this kind of extreme events. This was a wave disturbance at Hopkins Marine Station back on January 11th of 2001. We had what we like to call the big wave event here. To tell you how big it was, the significant wave height is a statistical descriptor of how wavy the ocean is. It's the average of the highest 1/3 of waves. So on that particular day, we had a significant wave height of 2.8 meters. In the course of a day, that's an average. In the course of a day, the highest wave you get would be about twice the significant wave height, or pushing 6 meters, or about 20 feet. So here at a moderately protected shore, we were getting waves 20 feet coming in. Now the period of those waves was also a little bit higher than normal. Normally the waves here are about a 9-second period. They were pushing 12 seconds there. Those conditions are in the top, maybe 3 or 4% of waves we get in a year. But that way we get 3 or 4 of those wavy kind of days in a year. What made this exceptional was that those high waves with long periods occur with the highest tide of the year, an exceptionally high tide. We nearly lost the caretaker's cottage just back out here, and rocks that we thought were part of the bedrock, rocks weighing up to 3 or 4 tons, were being tossed around. One got tossed about 10 feet up and 20 feet back in without touching anything in between. So that particular set of waves did a lot of damage out on the shore, and you can still see the effects of it now almost a decade later. So the question is, how often do those sorts of things happen? How long would you have to wait to get this kind of event again? So that average waiting time is what you refer to as the return time. It's an expression of the probability of getting this kind of extreme event. Well, to ask that question, it's a difficult thing to do. We tried throwing the usual statistics at it, couldn't come up with a good way of figuring it out. So we had to come up with our own statistics, what we're calling an environmental bootstrap procedure. Essentially what we do is take a short period of time, in our case 7 years worth of environmental data, and roll the environmental dice and see what would happen if chance played out differently. So we take the predictable part, take the unpredictable part, combine them as if we were replaying that year, just with a different set of chance coming along, and come up with a hypothetical year. See whether we get those sets of conditions or not. And we can do that thousands of times. Often we do this 10,000 times, and asking what percentage of those years would you get those kind of wave conditions. That's an expression of the return time or the probability of getting those sorts of extreme events. In this particular case, it turns out that we would expect those kind of wave events once every 28 years or so. So it really was a pretty rare event that we saw. I'd like to give you another example of this kind, the applicability of this kind of thing. This is Ladia gigantea, the owl limpet that you get here. Biggest limpet out in the shore. It's territorial. It maintains an area on the rock. It's garden. It keeps other things out and scrapes the algae off that grow in that garden. Being territorial, it returns to the same spot on the rock every low tide. So if on a good low tide where there's high air temperatures, it doesn't run away and hide. It just puts up with it, and it has the potential of overheating. So how often does a limpet like that fry on a shore here just through chance occurrence of normal events? Well, this is something that we can model mechanistically. Basically, we can model the body temperature of that kind of limpet by assuming that it's in equilibrium with its environment. So it's heated up by the sun, it can lose heat to convection, evaporation to the rock underneath it. Its body will assume a temperature where the heat in is equal to the heat out. So that kind of heat budget model allows us to measure body temperature as a function of environmental parameters that we have in that 7-year record of what the environment was like. In this case, rather than wave height, wave period, and tidal height, we've got 6 different things that contribute to body temperature. You have to have a sunny day, higher temperature when the tide and waves are low, otherwise it's going to get cooled by the water. Wind speed has to be lower, it can lose heat to the air. So we've got 6 different things that we put into our heat budget model, and out comes a body temperature. So we can take a hypothetical year, calculate what the maximum body temperature would be, replay that year, roll the environmental dice, see what it would be the next time chance plays out differently. And from that we can create this kind of graph. On the y-axis here we have body temperature, maximum body temperature you would get in a year. And on the x-axis down here we've got the log of how long you would have to wait. So 1 year, 10 years, 100 years, up to 10,000 years, this is what the maximum body temperature would be, or the probability of getting that. So if you look at a limpet on a north-facing rock, the blue triangles here, in an average year it's going to get to a body temperature of 22 to 23 degrees. You'd have to wait 10,000 years to get a body temperature above 35 degrees centigrade. But if you're on a south-facing rock, in an average year you're going to get it up to about 28 degrees. If you wait 10,000 years, you're pushing up to 45 degrees. So this is the probability of seeing a certain body temperature. To tie this to biology, we then need to know what the physiological capability of the organism is. So we go out, get some animals, heat them up the way they would in the environment, and see what their thermal capabilities are. So for these guys, you get them to 33, 34 degrees centigrade and they're starting to die. Much higher than that, you kill a larger fraction of the population out there. And we can combine this thermal capacity with the likelihood of seeing a certain temperature to come up with this kind of graph. Now on this axis, the vertical axis, we've got what fraction of the limpets are killed as a function of how long you wait for chance to play out. So in a typical year, nobody's killed. These things don't come into coincidence, and nobody's going to get fried. Even if you wait 1,000 years on a north-facing shore, you still kill a negligible fraction of the limpets out there. But if you live on a south-facing shore, it's different. Again, in a normal year, nobody cares. But about once a decade, you're going to see this kind of chance coincidence where upwards of 70 or 80% of those limpets will be killed. So we can go out there on the rocks now and notice that there aren't limpets on south-facing rocks. We can go out and measure in a typical year and say, well, the temperature didn't get high enough, maybe temperature doesn't matter. What this does is give us a window into long time, into the future if you want to think, that says, okay, once every decade or so, the limpets on the south-facing rocks get wiped out. Maybe that's why they aren't there now. The other thing that this approach allows us to do is ask the sorts of what-if questions that are valuable for thinking about climate change and potentially about policy. So we can ask, for instance, what if everything else in the environment stayed exactly the same, but the air temperature went up by 2 degrees centigrade? Results would look like this. So again, this is the fraction of limpets killed versus time. Now this isn't on a log scale, this is just an absolute scale here. And this is for limpets on a horizontal surface. So for the conditions the way they are now, that's the blue dots. It would take about 9 years, once every 9 years or so, you would kill about half the limpets out there. If you increase the air temperature and everything else the same, that return time to kill half the limpets goes from 9 years down to about 2.5 years. So even though the absolute temperature that things get to, the extremes aren't going to be that much higher if you increase the air temperature, the frequency with which you're going to get those extreme events goes up. So that's something that allows us input into how climate change is going to affect these sorts of situations. So some quick conclusions. These sort of coincidences, where everything is normal, it just happens at the wrong time, can cause extreme events. And short-term data, in our case, 7 years worth of data, allow us to say things about decades or centuries. You can then take that environmental data and apply it to physiological data in a mechanistic sense. You can predict the ecological consequences of these environmental extremes. And when you start thinking about it, this method can be applied to a wide variety of situations, connecting organisms to ecosystems, allowing you to say something about the probability of seeing extreme events in the future. And I'll stop and thank the people who helped with this.
Okay, these are hard acts to follow. So, research in my group focuses on how marine communities work, especially in coastal systems. And so we focus on a variety of questions that have to do with interactions among species within communities, the effects of natural and human disturbances on communities, and then questions that relate to how we conserve and manage communities, in particular focusing on the design and evaluation of spatial management approaches like marine reserves. And then another question that we're very interested in, and there are a lot of people working on in the lab, is basically what leads to successes and failures in management of fisheries, particularly small-scale fisheries. So these are what we do. And I want to step back and sort of reflect a little on how science contributes to decision-making. I think a key role of science is in fact to inform these decisions, not direct them, but inform them. And there are at least 3 ways by which science does this. One is by contributing to the understanding of how systems work. Another one is by analyzing and synthesizing data, so that essentially generalizations can be produced. And also a third way is by developing predictions about future scenarios. And essentially is, in terms of policy management, statements about if you do X, Y is likely to happen with a probability attached to this. So as an example of that is relevant to climate change, these are 2 statements from the IPCC 4th assessment report that concluded that is in fact very likely, 90 to 99% probability, that temperature increases documented globally are linked to increasing greenhouse gas concentrations of anthropogenic origins. And then what the scientists involved did is select 29,000 time series and synthesizing the information essentially available and concluding that 90% roughly of the series where significant changes had been seen over at least 2 decades in some biological or physical parameters actually were in the direction consistent with what you would predict under climate change scenarios. And then more recently, a couple of weeks ago, this is the Climate Change Science Compendium that the UN Environmental Program put out, which actually shows, or at least concludes, that the rates of increase in anthropogenic fossil fuel emissions that we've seen in the last 7 years is in fact exceeding the worst case scenario of IPCC. So in the spirit of trying to assess what is the big picture of how climate stressors, but also all of the other ways in which we're influencing the ocean are affecting marine ecosystems, a few years ago with my former student Kerry Capel and Ben Halpern from ENSIS in Santa Barbara and several other collaborators, we embarked in this project, which is actually very different from what we normally do as community ecologists. And we set out to try to quantify and produce visuals of what the cumulative impacts of multiple stressors to the oceans are. And so what the science, where the science comes into place here is in the work of assembling the information and then developing an approach to put it all together. So all the decisions that have to be made in creating a model essentially, and then that allows us to draw some conclusions about our cumulative pressure to the oceans. So we assemble global data on 17 different types of activities or associated stressors, including climatic stressors, fishing, pollution, and so on. Data on the distribution of 20 different types of marine ecosystems, and then we developed a method for accounting for the differential vulnerability of marine ecosystems to these different pressures. And so the climate change stressors that we were able to include are here depicted in these maps with a color scale that is proportional to the magnitude of this measure of these variables. For example, here, collaborators in this work calculated the frequency of temperature anomalies using a 20-year data set, the Pathfinder remote sensing satellite data, looking at essentially the frequency when surface temperature exceeded one standard deviation around the 20-year mean of temperatures. So this is the frequency of the hot events. Similarly, UV radiation increase, the frequency of positive anomalies in UV radiation from NASA data sets. These are data provided by John Pinot, who modeled the arrival and saturation state in the oceans from pre-industrial times to the last decade. So these were the 3 climatic stressors, and then as examples of other possible stressors, these are global data on the extent, distribution, and intensity of commercial shipping activity, and we had 5 categories of commercial fishing types, and this is trolling, for example. This is data analyzed by the Sea Around Us project in UBC. Then to develop a vulnerability criteria, we essentially decompose the characteristics of the impact of a stressor on an ecosystem into 5 components. The first 2, spatial scale and frequency, have to do with the interaction of the stressor with the ecosystem. What's the spatial extent of that interaction? How frequently does that occur? Then there are 2 components that have to do with the response of the ecosystem, and essentially how many trophic levels are affected, which is functional impact, and what's the percent loss in biomass in that ecosystem as a result of the exposure to the stressor, and then recovery times. And so all of this was combined in a vulnerability wage, which is a relative index that tries to capture the differential vulnerability of a seamount and a soft bottom to trawling, for example, accounting for the different sensitivity. Because this information is not available for a number of all the possible ecosystem stressor combination, we use both surveys of the literature and expert surveys to develop the score. So in the end, we layered the maps for the stressors on top of the ecosystems. For each kilometer square of the ocean, we apply the vulnerability weight to each combination, and so then we summed everything up to obtain a cumulative impact score for each pixel of the ocean, and then we assign the scores to categories ranging from very limited or no impact to highly impacted systems, based on an assessment done for 14 coral reef ecosystems on their state of degradation that we correlated with other scores. So I synthesized a lot of method, but very quickly I'll walk you through a visual here. So to orient yourself, this is Washington DC Cape Cod of how this works, and also to give you a sense that some data are actual measurements, some are modeled. For example, if you start from the land, what Sean Waldridge at ENSYS did is to develop a layer with the watersheds, and then we obtained fertilizer use data from the FAO. Fertilizers were spread across the landscape based on data on land use, where there's agriculture, where there's urban development, and then they were poured using the information from the watershed at the mouth of the watershed. So this is the footprint of fertilizer use, is showing in a color scale the concentrations of input of fertilizer, and then to calculate impacts, we turn the footprint into an actual impact using the information about what ecosystems types are found there and the vulnerability weight, and then you do this for all of the different stressors, and then calculate the cumulative impact score. So the resulting global map shows that based on all these decisions that we made, basically on how we structured this research, we conclude that a large portion of the ocean is heavily impacted. Few places remain that don't have significant impacts. The US, if you're looking at that right column, actually is slightly higher than the global average, with about 2/3 of the US EEZ that we consider, based on our classification, as medium to high, very high impacts. These high scores that we're seeing in cumulative impacts are typically, with a few exceptions, the result of several different layers overlapping rather than having one major pressure. And in fact, in coastal areas, for example, we had 10 or more different stressors overlapping in each pixel. So very high level of impact from multiple stressors. Very briefly, basically, I wanted to make the point that in our model we assume that these different impacts add, when in fact there are no additive effects, and this is work done by others in the group that show that non-additive effects are very common, and so we could actually expect these estimates to be conservative or to be overestimates, depending in some cases, but there are results, some uncertainty. So the implications of these results are that marine ecosystems are affected by multiple stressors to a much greater extent than we anticipated. This, in fact, in the context of climate change, may be very important because the ability of species and ecosystems to adapt and respond to climate change may be impaired because systems are subjected to so many different threats, and so that a management objective should be to address individual stressors, but ultimately to reduce the cumulative level of impacts, and then this can be done, we argue, only through comprehensive spatial planning of activities. So, very briefly about essentially, with these results, we went to Washington, D.C. and had briefings in Congress and various people, including Sam Farr and Lois Capps and Josie. And so this is a mechanism by which, essentially by conducting science that is synthetic and looks at the big picture, I feel that's an effective, not the only way by far, but it's an effective way of conveying the message to policymakers.
Just before I talk, I just wanted to again welcome you to the Hopkins Marine Station and say that we all here find the marine program to be incredibly exciting. It really stands to open the door to a broad kind of education among all of our graduate students. And that this seminar and this whole series tonight is just the beginning of a conversation that we hope will last for a very, very, very long time. And I especially want to thank Meg Caldwell for Costa's interest in putting this all together, but also the people that really spent a huge amount of time as the representatives from all our campuses to make this happen. I don't know how many times in academic life you've heard somebody say, wouldn't it be nice if something like this happened? And how many times that never does occur. And this is one time when somebody said, what if this happened? And it really is happening. I think that's really amazing. And part of this is being able to take courses. Part of this is actually talking with one another across disciplines. And what I'm going to talk about is the work that we do in climate change, and particularly in genetics and in connectivity in the oceans. But I also spent a great deal of time last night thinking about climate change, science, and policy. I got very depressed about that. I'm not going to try to depress you about it, too. I'm going to try to alarm you about it and provide you with what I think is a true, complete puzzle, and what I think might be a little bit of the crux of the problem and what it is we're trying to do as scientists, but also as citizens and as people who have to live in the world. The world changes a lot environmentally. Ecosystems do change. We've heard a little bit about this earlier. One of the ways that ecosystems change with the climate change are biogeographic shifts. These are well known across the world. This is just a figure based upon the Audubon Christmas bird count of the kinds of biogeographic shifts that have happened in bird species across North America. Where do they go? North. When the climate gets warmer. People have seen this in plants, they've seen it in land mammals, they've seen it in lizards. They've also seen it in marine fauna. This is a paper by Chung et al. That just came out in Global Change Biology, and it looks at the predicted shift of fish species around the world when global climate change raises the temperature by 1.5 degrees. It's based upon the way that fish use their environment. And red on this map means that there's a net increase in fish species in the north from the south. And over here is just a view of how fast there are latitudinal changes in species distributions in fish, demersal and pelagic fish, compared with birds and butterflies that we looked at before. So the migration rate of species in the ocean is likely to be very large and head north. But not all species can move this way. These are fish. The Sea Around Us project worries about fish. But there's lots of other species out there that aren't fish and that may not be able to move quite so well. In particular, part of what we do in my lab is work on coral reefs, partly because coral reefs are a very, very nice ecosystem that capture people's attention, but also there have been predictions laid out there over the last 10 years that coral reefs will be dead soon. 50 years, 30 years, some time frame like that, due to warming, acidification, and pollution, all those combined stressors, just like Theo was talking about. Well, one of the ways that corals might be responding to global climate change might be moving and shifting their biogeographic ranges, and so we started to look at connectivity patterns of corals across the Pacific as a consequence of that. We've been looking at the genetics of corals throughout the Pacific, but I want to focus on this that we call the Southern Cross here. The Tuvalu and Tonga are north-south transects, Samoa and Fiji are east-west transects, right about just south of the equator. What we've been doing is looking at the genetics of these populations to try to understand how much migration there is normally in this kind of area and how that relates to the potential for shifts in shifts after global climate change. We do this by looking at the distribution of genetic variants, and in this particular case, a tabletop of coral. What's shown here are pie diagrams that show the distribution of different alleles, and one particular genetic one, this happens to be a PAC-C intron, and the colors are stacked up very nicely by Excel to be the same in the different places. And what you can see is that the colors are a little bit different, but there's a lot of this purple stuff on both sides here. Between American Samoa and Fiji, in any case, there are genetic differences between these populations. They are not the same, but a lot of the alleles are shared, and there's a relatively large amount of gene flow east to west across this particular area. If we then go to Tonga and Tuvalu, what we see is a different situation, because there the distribution of genetic variants is quite distinct. there's all this red that pops up in Tuvalu. That's a genetic variant that's quite rare elsewhere. And then down here in Tonga, a set of genetic variants which occur elsewhere but at very low frequencies. The amount of gene flow expected on this basis is actually relatively low. In fact, the north-south gene flow is really very, very, very low compared to the east-west gene flow in this particular comparison. Why might that be? Well, that might be because that's the way the currents flow. In fact, this is just a sort of map that you can pull off of an oceanographic atlas of the various current patterns in the Pacific. They all go east-west because they're run by gyres. The north-south currents are mostly along coastlines, along continents on the side. But in the middle of the Pacific Ocean, most of the currents go east to west, and so this probably explains why we see these patterns of gene flow largely east to west across the Pacific, not north to south. Response to climate change needs a north-south migration response, not an east-west migration response. And it's possible that because of this sort of thing, the ability of these types of animals, corals across the island nations of the Pacific, the ability of those populations to respond to climate change might be curtailed. So that suggests that, in fact, these kinds of populations will respond differently than other like fish, and that they may be more vulnerable because they can't escape by heading to the poles when things get warm. But this is the kind of information that will motivate great leaps in policy. It's good biology. It's the kind of science that we like to do as individual scientists. We can write grants and papers about it. But is it going to change the way the world burns fossil fuels? And the answer is, of course not. It's not going to change. A little perspective, though. What will change how people act is the question. A little perspective is that, in fact, the world is changing. Sea level is going up. In particular, it's gone up about 9 inches in the last century around here. We can predict this. The IPCC has gotten a lot of bad press in the last couple of years, but in fact, their prediction of global sea level rise, which is these 3 numbers, is pretty much bracketing the real observation of sea level rise over the last 15 years or so. So their ability to predict sea level rise is actually really good. Now, the next prediction is that over the next century or century and a half, sea level rise is likely to be a meter or so, maybe a half a meter, maybe 2 meters, depending upon things like ice. But just the thermal expansion of the ocean will bring us about a meter of sea level rise. We can begin to look at how that's going to impact the infrastructure of the West Coast, not necessarily the ecosystems, but just the infrastructure, by looking at what will be left with an extra meter of sea level. So this is what goes away when sea level goes up a meter. Let's go back. That's the way it is now, and that's the way that's where a meter of seawater goes. Take a look at what happens down here in the South Bay. Everything bayward of 101 is underwater. Everything bayward of 880 is underwater. Everything north of 680 is underwater with a meter of sea level. That's the prediction. A prediction of the IPC is you've got a good track record for, and it's probably very conservative. If you go to Google and say, what lives between 101 and 880 and 680, there's an enormous amount of real estate. Plus, there's some biogenic habitats, there's some marshes, there's some really important ecology, but there's $250 billion worth of real estate there that is going to get flooded out. Now, I look at this as a biologist and say, if policymakers look at that and say, that isn't enough to motivate change, then these marshes are never going to be enough to motivate change. So what I'm going to try to leave you with is this quandary. We can do the science of global climate change, and it's important to do because we need to understand the mechanisms by which climate change affects the biology on Earth. And I think the work that you've heard today has a lot of things to say about those mechanisms and how we can use them to predict what's going to happen. But we'd be fooling ourselves by thinking that understanding how climate change is going to affect the dispersion of corals like we do, we'd be fooling ourselves into thinking that that's going to motivate climate change policy when this doesn't. Now, what is part of the answer to that, and what I'm going to have put up in the panel discussion is part of that. And I would say that part of the reason why there's this huge problem is that no matter what we say to each other in this room, people don't believe it. They don't think the world is falling. They think they're going to be able to escape. This is an opinion piece published by 2 Stanford undergraduates in the Stanford Review last week that basically says any practice intended to reduce hydrocarbon fuel burning is a futile inconvenience, which is a beautiful balance to an inconvenient truth, right? So what are we going to have? We're going to have an inconvenient truth or a futile inconvenience. That's the argument that we're going to have to face. It's not just the policymakers, it's not just the legislators, but it's in fact to the entire general public. And what I want to leave with is that part of what this group Marine does is really important. Why? Because it creates research? No, because it creates education. And one of the things I think that we can talk about later too is that none of this is going to work. No science will turn into policy without a scientifically literate group of political, social, and economic leaders. I'll say that again. A scientifically literate group of political, social, and economic leaders. Do we have that? That's one of the things we have to move toward.